Let us see the important topics of semiconductors chapter for NEET exam 2024. If you see the classification of semiconductors, chapter, okay, the topics that are considered in the semiconductors chapter, okay, mainly diodes, okay, and logic gates. Diodes, including their applications, okay, and working, biasing, characteristics, all properties regarding the diodes. Logic gates, types of logic gates. General logic gates will be there, universal logic gates will be there, okay. So universal logic gates we have to discuss. Using universal logic gates, how to construct the general logic gates also topic is there, okay, that we have to learn for the NEET purpose, right. So if you see the diodes first of all, right, generally it is also called PN junction diode. It will have first construction. How to construct it, that is construction. Next, biasing a diode. Of course, forward bias, reverse bias, when it is said to be in forward, when it is said to be in reverse, okay, that biasing, and behavior of the diode in biasing, okay, that is, we can say, behavior of diode in biases, okay, that is in forward bias, how it will behave, in reverse bias, how it will be, okay, when there is no bias and what happens, okay, what happens to the potential barrier inside it, threshold, the depletion region inside it, okay, what is the drift current, what is the displacement current, what is the diffusion current, not displacement current, okay, what is the diffusion current. Displacement current will be there in case of capacitor, EM waves, okay. So here in case of diodes, drift current and diffusion current, only two things will be there. What are those? What is the expression for them? That thing they will ask. And next, after seeing the behavior, like characteristics, we have to understand that. Characteristics means like forward bias we have to give, and we should increase supply, and after by increasing the supply voltage we should measure the current, okay. Then what is happening to the current throughout the range of voltages that we are varying, that plot is a characteristic graph of that, okay. So from the characteristic curve also they will ask the question, the resistance of the diode in forward bias and also reverse bias they will ask. The resistance in the sense, like if it is forward bias characteristics like this, then the slope of this diode, this graph will be 1 by resistance of the diode is in forward bias, remember, reciprocal, and this is in forward bias, okay. And reverse bias you have already seen, this will be the reverse bias, okay. In reverse bias also the slope will be equals to 1 by resistance of the diode in reverse bias. And in the reverse bias there will be breakdown also, the breakdown voltage, okay. At what voltage the diode is breakdown, and there are two types of breakdowns again, avalanche breakdown, Zener breakdown. What are those? You have to understand that, right. So thing is the characteristics regarding the diode that we have to understand. After that, if you know the ideal diode and non-ideal diode, in forward bias and reverse bias, how to draw the equivalent circuit diagram of ideal diode and non-ideal diode, you have to understand that. That I have already explained in the class, okay, that you have to read, that is important topic I am saying, okay. That is the effective circuit diagram of diode in case of forward bias and also in reverse bias, in case of ideal and non-ideal cases, okay. So that you have to remember, right. This is about the diode. If it is, if you go to the applications of the diode, the one and only application is a rectifier, okay, that we can discuss in the +2 level is rectifiers. But there are three kinds of rectifiers. One is half-wave rectifier, in short HWR, another full-wave rectifier, and then bridge rectifier, okay. In this, out of these three, if you understand the full wave rectifier, it's enough to discuss the, remember the half wave and bridge rectifiers, okay. So I prioritize this full wave rectifier if you understand, that's enough, okay, and remaining things will be easy. And for bridge rectifier, circuit diagram alone is different. You have to remember the circuit diagram for bridge rectifier, where the 4 diodes will be used, okay. And in case of half wave rectifier, in case of full wave rectifier, you should concentrate on IDC, okay, and IRMS, IRMS like RMS value of current, DC value of currents, voltages, peak inverse voltage, okay, output and input frequencies, ripple factor, efficiency, all this, okay, in case of full wave rectifier. You should not miss in a single formula also, right? And you should also understand the importance of, center tap in case of full wave rectifier. Half wave rectifier, it has no center tap. Full wave rectifier is having center tap. But the advantage of full wave rectifier is the ripple factor of full wave rectifier is less than the half wave rectifier. Okay, but the disadvantage is the cost of construction will be more as compared with the half wave rectifier, because it required center tap there. Okay, center tap, if you want to construct, it will be more. It will be having more financially expensive than the half wave rectifier. So only we will go for the bridge rectifier. Okay. So that's the reason bridge rectifier is preferred over the full wave rectifier. I hope you got it. And this is the only one and only application. Okay, there is no other application. But if you go to the special purpose diodes, okay, LEDs, Zener diode, and also photodiode. Okay, 3 things we'll discuss: LED, Zener diode, and photodiode. Okay, in this photodiode, solar cell also will be there. You should not forget this. So in this, out of all these 3, Zener diode is very important. Okay, and Zener diode as a voltage regulator is very, very important. Okay, circuit diagram regarding the Zener diode. Okay, Zener diode as a voltage regulator also you have to discuss, right? Differences between the Zener diode and normal diode you have to understand. Okay, and the question they can ask, out of all these LED, Zener diode and photodiode, they will ask you that which of the following are used in reverse bias. Okay, the options may be LED and photodiode, LED and Zener diode and photodiode, any of those above. Okay, and you should remember, if you read the NCERT or if you attend my class, it will be easy to remember that. Okay, that is, LED is in forward bias actually. Zener diode and photodiode generally used in reverse bias. Okay, to give the special properties. They can also ask the question here: can you use the Zener diode and photodiode in forward bias? Yes, of course we can use, but the special properties we will not have in case of forward bias. Okay, what is the special property of Zener diode? Voltage regulation is a special property. That will not be possible when it is connected in the forward bias. It is possible only when it is in reverse bias. Similarly, photodiode, it has to generate the electricity, EMF. Okay, it has to produce a EMF by converting light energy into the electrical energy. And that is possible, effectively that is possible in reverse bias. Okay, forward bias it is comparatively less effective. Okay, that's the reason Zener diode and photodiode generally used in the reverse bias. I hope you got it. Okay, these are the applications that are important, you have to remember. And going to the logic gates, I told you already, there are 2 types: general logic gates, universal logic gates. Okay, general logic gates are 5, universal logic gates are 2. Okay, but in the NEET recent updation of the NEET syllabus, they have removed the XNOR gate. So general logic gates only 4 they given, universal logic gates 2 they given. Okay, right? So the general logic gates, if I list out: OR gate, OR gate, AND gate, NOT gate, XOR gate. Okay, OR, NOT, AND XOR gate. Okay, and the universal logic gates will be XOR gate. Universal logic gates will be NOR gate and NAND gate. Okay, and the important thing is, using universal logic gate, you have to construct the general logic gates. Okay, using only NOR gate, you should construct the 4 remaining gates, or using only NAND gate, you have to construct the 4 remaining gates. Okay, how to construct I have already explained. You have to focus on this definitely the question will be coming from here. Okay, and then logic operations using bulbs and also diodes. Okay, suppose by using bulb, can you construct OR gate? Can you construct AND gate, NAND gate, NOR gate, NOT gate? Okay, and can you construct the same gates by using diodes? Okay, this topic also you have to remember, right? I hope you got the clarity. A diode. So what is a diode? I already know that, but I have told you that it involves the construction and biasing, working, okay, and of course special purpose diodes, everything. Let us see. Construction is very simple. It has two parts. One is P term and another is N, and it is P terminal, N terminal, and here it is the majority charge carriers are holes, and here it is electrons, right? And PN junction diode is formed by taking the two semiconducting materials, that is P term and P type and N type materials. Okay, this you know already. Here this is called as junction, which is this is called as junction. Of course, here there will be depletion region where there are no charge carriers. Okay, in this region no charge carriers will be there. This is called depletion region. Okay, and across the depletion region there will be barrier potential also. Barrier potential. The charged particles duty is to cross the barrier potential and then enter into the other regions. Okay, how to cross the barrier, that depends on the external supply that we are giving. If you make P positive and N negative, then it is forward bias. If you make other reverse connection, it is going to be reverse bias. Okay, so let us consider one example here. Let us say there is a circuit. In this example, I am giving the explanation of all possible situations of the diode. Okay, so just consider this experiment. Say this is a diode 1 and the resistance is here, and this is second diode which has another resistance over here, and say this is a common resistance this way, and this is diode D1, diode D2. And there are two cases, I told you already. Ideal diode, case 1 is ideal diode. Say this supply is 10 volts and this resistance is 2 ohms and this is 3 ohms, and let it be 4 ohms. If the diodes are ideal, you must know in ideal case forward bias what happens and reverse bias what happens. Okay, or before going to see the ideality or non-ideality, you should first figure out which of the diodes are in forward bias and which is in reverse bias. Okay, diode D1 will be in forward bias. Okay, D2 is in reverse bias, right? And now coming to the ideal diode case. Ideal diode stands for, in forward bias, I told you already, it will be closed circuit. What is meant by closed circuit? This diagram will be closed circuit, resistance is as it is. But reverse bias, it is open circuit. The diode D2 is in open reverse bias, so it will be this way. This is 2 ohms and 3 ohms, 4 ohms. Through the upper branch, no current will be there. Through this branch only current will be present. Supply voltage is 10. Then apply the Kirchhoff's law or Ohm's law. The 10 volt supply should be equals to 2I plus 3I. It is equals to 5I. Then I equals to 10 by 5. It is going to be 2 amperes. Okay. This is when the diodes are in ideal diodes. Okay. If the diodes are non-ideal, let me consider the situation also. Let us see if the diodes are non-ideal, what happens. Okay, if the diodes are non-ideal, right? So it means in forward bias the resistance is not equals to 0. They will have a non-zero resistance in case of forward bias. So we have to figure out which is in forward bias and which is in reverse bias. Okay, wherever the diode is in forward bias, you have to consider a potential drop across it. Reverse bias, it is as it is, like in case of ideal diode or non-ideal diode, reverse bias will be same thing. It is this is 3, 2 or maybe something like that, and this is threshold voltage. The supply voltage is 10 volts. Then threshold voltage V naught you have to consider. Then supply voltage 10 volt equals to 3I plus V naught plus 2I, where I is a current through this. Then I equals to 10 minus V naught by 5. What is the V naught? It is a threshold voltage, right? Yeah. This is case 2 when the diodes are non-ideal. I hope you got it. And going to the applications of diodes, Zener diode as voltage regulator. Zener diode as voltage regulator. Remember, the total current is Zener current plus load current. Sum of the two we have to take. There are two possibilities that you should understand. Case 1, when supply voltage is varied, then the total current will be changed, load current will be changed, but Zener current will be remains same. The total current will be changed by same amount, Zener current will be changed, okay, but the load current remains same, because the diode, Zener diode as a voltage regulator, output voltage must be constant. So only if supply voltage is increased or decreased, accordingly total current will be either increased or decreased. By the same amount, Zener current will be changed, but load current will be remaining same. This is case 1. Case 2, keeping the supply voltage constant, we are changing the load resistance. If the load resistance is changed, then load current will be changed. Accordingly, Zener current will be changed, but total current will be remains same. Okay, that means the load resistance changed, then load current will be changed, and Zener current will be changed, but the total current remains constant. Okay, so that is case 2. So let us consider one situation here. Say this is a variable supply, okay, and it can be varied from 40 to 120 volts. Okay, minimum value 40 and maximum value 120. The Zener voltage is 30 volts, say, and the load resistance is 1 kilo ohms. Okay, and the series resistance, say 1500 ohms, right? Then we can change the supply voltage from 40 to 120 any value, but Zener voltage is 30, which should be fixed, and always voltage across the load resistance must be 30 volts only, because after the breakdown voltage across the Zener diode is breakdown voltage, and load resistance is connected across the Zener diode parallelly. So this 30 volts must be same forever, right? That is how the Zener diode will be worked. And going to the rectifiers, I told you already, the full wave rectifier, half wave rectifier will be there. In that full wave rectifier, efficiency formula, based on efficiency formula only they will ask, okay. So 0.812 into load resistance by load resistance plus forward resistance, this RF. And if the efficiency to be maximum, then RF to be 0, ideal diode it is. Okay. Then eta maximum is going to be 81.2 percentage, right, 81.2 percentage, right. And of course here ripple factor will be there, which is equals to 0.48, ripple factor is 0.48, and which is less than the half-wave rectifier ripple factor. And next, going to the logic gates. Okay, universal logic gates. Universal logic gates. NOR gate, NAND gate. Okay, NOR gate and NAND gate. Using NOR gate, how to construct the all remaining gates? Let us discuss. Using NOR gate. If you are using only NOR gate and your intention is to construct the remaining all gates, then how to use that? First of all, using any universal logic gate, it will be very easy to construct the NOT gate. Okay, so case 1, NOT gate. Just consider a NOR gate this way and couple the inputs. This is A, output is going to be A bar. This is NOT gate. The next easiest part using NOR gate is OR gate. OR. Okay. So remember, even number of NOR gates will give you OR gate. Even number of NOR gates cascaded A plus B whole bar. Here A plus B bar, again bar cancels. This is A plus B, right? I hope you got it. This is OR gate. If you connect one more, it will become odd. Odd means it is NOR again. Next, third part is NAND gate. Using NOR gate, you should construct NAND gate. Okay, it's very simple circuit diagram. This way. If you can see here, all are NOR gates. A, B, A bar, B bar. Here A bar plus B bar whole bar. Then it will give you AB. It is OR gate. Okay. So we have constructed all the three gates. And what about XOR gate? XOR gate is a fourth case. Exclusive OR gate. Exclusive OR gate is very simple. You have to place these diagrams like NOT gate, AND gate, NOT gate, AND gate, OR gate. So in place of AND gate, you have to substitute this, and here also, and NOT gate place in case of NOT gate you have to use this, and OR gate you have to use this diagram. and finalizing that will give you the XOR gate. Next, one more way of asking the questions from this, they will give you the waveforms. The waveforms they will give. Say this is A, 0 level of A and 1 level of A. Like this they will mention. Waveforms. And B, say this is 0 level and 1 level. This time they may give this way. Next, output 0 level and 1 level. The output they will give you, okay, and they will ask you to find out which operation it is, okay, which operation the gate they will ask you. It's very simple, the output, okay. Let us consider the output 0, 0, so let it be 0 and it is 1, 0, 0, okay. So this is output, and if you can see this, first A 0, you should make the truth table here, okay. A 0, right, B also 0, output is again 0, this is 0 only, and next time it is A is high, that is 1, B still remains 0, so 0, output is again 0 only, so 0. Similarly, here third gap, the A came to 0, okay, and B gone high, output is a wrong output I given here, I am sorry for this, just a minute. Output I should have given this way. Only, yeah, at the instant when both are high, output is high, they will give you correctly. Yeah, so A0, B1, but output is low, this way. Now as soon as A is high, B is also high, then output is high, 1, 1, 1. And next A low, B low, output is low, 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 low. And then A is high, B is low, output remain low. A is high, B is low, output is low. So if you see all these configuration combinations, whenever inputs are high, both inputs are high, the output is high. This is which operation it is? AND gate. Okay. This is the AND gate operation. Like this they can ask the questions. And let us have one more example based on this. They will give you the waveforms, but instead of giving the output, they will give you the diode, they will give you the logic gate, and they will ask you the output waveform they will ask. And that's very simple. Yeah. Say the A waveform they have mentioned this way 0, 1. B waveform they will mention and this is given to a logic gate, which is this gate A, B. It is OR gate, okay, very clear for us. Then output will be what? The question is about the output only, right? So first of all, OR gate is addition. When any one is high, output is high. Okay, so you can see this. First, A is low, B is low, right? So A low, B low, output must be low. So it should be this way. Then A is high, it's gone high, okay, but B remained low. Then output should be high because 1, 0 should be 1. And after that A became low, B is high, but output should be high because at least one input is high, output should be high, okay. So until last it will be high only because after this instant at least one out of A and B are high, so we can say the output will be high after this instant. Okay, so this can be the questions, this can be the question they can ask. I hope you got it. Next thing, using bulbs, how to construct the logic gates. Using bulbs, okay. Let us suppose we are constructing OR gate. OR gate is if at least one input is high, output should be high, okay. So this is a supply. We can construct this diagram and bulb is here. When bulb glows, the output is high, okay. This is input A and the input B, key is there, okay. If at least any one key is closed, then output will be there, okay. So this is OR gate. And in the exam they will give you a question like this, they will mention. Okay, so which gate it is? It's very simple. A, B, if both are high, then only the bulb will glow. Okay, if both are closed, then only output will be high. So we can say it is AND gate. Directly we can say. Similar to this, we can have one more. Right. So A and B here, if any one is high, for example, if any one is high, then this bulb is short circuited. If any one is high, then output will be low. Or we can say if both are open or if both are low, then output is high. So if both are low, output is high, it is something like NOR gate it is, okay. A plus B whole bar. A plus B whole bar is 1. Okay, that is going to be, if any one is high, if any one is closed, then output will be low. So NOR gate it is. Okay, so this is how we have to construct the logic circuits, logic gates using the bulbs. Okay, suppose if the question is about the constructing NAND gate using bulbs. Using bulb NAND gate you want to construct, then how it is? Okay, that you can do it for yourself. Okay, suppose there is a gate which has been given this way. This is input A. Now it's very clear, if A is open, that is A is 0, output will be high. If A is closed, A is 1, output will be low. So it is not operation. Right? So like this, you can get many questions. Okay.